sorry about that, but there's the proof. That's really all we've done is go through that proof. All right, any other questions? All right, you're going to love homework 5. All right, so I'm going to cancel homework 5 because we've got like lots of other stuff going on. Most of you have 2 midterms this week from me and possibly midterms from other classes. And you just finished homework here. We're deep in the ramp up of PA3 and we're switching topics here and talking number theory, and so I will postpone homework 5 and next week's homework, which I'll assign a week from today, we'll have some questions on number theory. But you know, it's kind of a short week anyway because we spent an hour on the exam and so on. So no homework this week for this class. So take a bit of a break. Hopefully that doesn't like kill anyone's weekend because they were hoping to spend the weekend doing homework.
Really a huge downer.
I know. Sorry. All right.
I'm going snowboarding.
Excellent. Where are you going?
Mount Hood.
Nice.
No, that's actually perfect because it gives me more time to work on physics.
Ah, cool.
Well, we get to do that all over the weekend instead.
You could do physics while you're snowboarding, technically. I mean, that could be like a fun way to... No, probably not. All right. So let's continue with number theory. And let's just touch base on some of the open problems that that we'll run into, and some of these may tie into other things you'll be doing in this course. But you know, number theory, it's arguably such a simple topic. We're talking about numbers, 1, 2, 3, 4, 5, right? And you can ask questions that involve, you know, adding or multiplying or dividing. But you can ask some questions that we have not been able to answer yet. And so so here's an example of an open question. We know what prime numbers are, right? They're numbers that are only divisible by themselves and 1. And if you look at prime numbers listed in order, you sometimes find consecutive odd numbers that are prime. 11 and 13, 17 and 19, 3 and 5, also 5 and 7. And 29 and 31. And so on. So when you have a pair of primes that are separated by 2, those are called twin primes. Now you're not going to find many primes separated by 1. Why is that?
I thought actually that makes the difference between an even and odd number.
Yeah, it makes the difference between even and odd. So 2 and 3 are unique. They're both prime and they're separated by 1. But once you find any other prime, you know, bigger than say 2, like 101, you know that if you add 1, you're going to get an even number, and that even number is going to be divisible by 2. So we're not going to find many consecutive numbers that are prime, but you know, 101 and 103, it's possible that both of those are prime.
Interesting. Primes are normally found in pairs, right? Or close to pairs?
Often not, no, and the number of pairs gets fewer and fewer as you increase, just because the number of primes gets smaller and smaller.
I thought that when they find primes, they normally find 2 of them, like, rather close in general. You know, could be millions of numbers apart, but...
It depends what you mean by close, yeah. So when you're out... Go ahead.
more than like, I don't know, the number before it. Like, they'll find, you know, they'll go like 40 million digits or whatever, and then they'll find 2 primes within, you know, a couple million.
I could believe that happens, and I don't remember, you know, reading about the details of something like that, but I could believe that happens, and that, you know, certainly the distance between those close primes increases. But yeah, I could believe that there's some sort of almost caching effect of once you found something that eludes all the possible factors below it, there might be other things relatively near to that. But being right next door to a prime, just 2 away, is pretty rare. But as far as we look, we always find, you know, eventually there's another pair of twin primes if we look far enough down the number line. But is there an infinite number of twin primes? We don't know. Nobody has proven that there are, but nobody has, you know, found a point beyond which we know there are no more twin primes. So it's an open question. And, you know, it's really easy to state. If you know how to divide things, you can describe what a prime is. But this problem has eluded a solution. So that's an open question. Another open question is something called Goldbach's conjecture. And Goldbach's conjecture is really easy to state. It claims that, you know, any even number bigger than or equal to 4 can be written as the sum of 2 primes. Any even number can be written as the sum of 2 primes. So 4 equals 2 plus 2, those are both primes. 6 equals 3 plus 3. 8 equals 5 plus 3. 10 equals 5 plus 5. It's also equal to 7 plus 3. 12 is equal to 7 plus 5. And so on. And any number that you try, you can do this for.
Even like the huge numbers?
Even huge numbers.
That doesn't make any sense.
Yeah, it doesn't.
Because like, once you get extremely far, you know, you'll find maybe a prime or 2 every, I don't know, what, quadrillion, billion.
Yeah, yeah.
Or whatever.
Exactly.
How is it that you could pick a number and add 2 of those primes together?
I think the main thing is that when you get a number that is that big, there are so many primes up to that number that you've got a really good chance that at least one of those, if you subtract it, you're going to end up with another prime. But it's...
Always 2 prime numbers?
Say again?
Always 2 prime numbers can add up to that?
That's the claim. And it's unproven, but nobody has found a counterexample either. Now, if you could find one even number, right, you could, and you try adding all the primes less than it, you know, and no combination of those gets you the number, that's all you need to say Goldbach's conjecture is false. To prove it's true, you'd need to either check every even number, and there's no limit to those, so you can't do that, or you need to come up with some kind of, you know, presumably clever proof, in the same way that we show there's an infinite number of primes, or the square root of 2 is irrational, or something like that. Nobody's been able to do either of those things. But mathematicians have put ridiculous requirements on a number that would break Goldbach's conjecture. And it's got to be bigger than, I don't know, 10 to the 40th or 10 to the 400th or something. There's some ridiculous lower bound on how big a number has to be to break this. But we don't know.
Interesting.
Let me show you another little, this is kind of a fun puzzle. This is called the 3n plus 1 conjecture. This is even simpler than questions about prime numbers.
Oh, this is fun.
Yeah, pick a number. right? Pick the number 5. If it's odd, multiply it by 3 and add 1. If it's even, divide it by 2. So 5, 3 times 5 is 15 plus 1. The next number in the sequence is 16. That's even divided by 2 is 8, 4, 2, and we finally end up with 1. And once you get down to 1, right, that's odd. 3n plus that would be 4 divided by 2 divided by 2. 4, 2, 1. This pattern is going to repeat forever. So the question is, if you do this for any number, right? If you start with 6, well, that's even, so divided by 2 is 3. That's odd. 3 times 3 is 9 plus 1 is 10. That's even. Divided by 2 is 5. That's odd, and so that's, you know, going to take us to this sequence, and eventually we're going to come down to 1. And so any number that you think of, you can apply this test and ask, you know, do we eventually come down to 1? Or do our numbers get bigger and bigger, or do they repeat at some value other than 1? And this is an open question. And this is another one of these questions that the analysis of it has led to all kinds of deep insights into the nature of numbers and other things. And it's a really simple question, right? If you take an odd number, if it's odd, multiply by 3 and add 1. If it's even, divide by 2. Keep doing that. Do you eventually stop? And it's a really easy problem to code, right? You can tell if a number is odd by seeing what it is when you divide by 2. So if a number %2 is equal to 1, it's an odd number. If it's equal to 0, it's even. And you can multiply a number by 3 and add 1, or you can divide a number by 2. So a few lines of C code, you can write a program that lets you, you know, type in a number n and shows you all the numbers that come out of that until you get down to 1. But no one knows if this always happens.
If you do it on the negative side, there's 3 loops.
Yeah, negative side gets weird.
So I think it'd be the same if you did 3n minus 1. Same as if on the negative side. Yeah, I think so.
That could be.
So yeah, 4, 2, 1 loop on this, and then there's 3 on the negative side.
Yeah, okay. Cool.
It's a very cool, very casual video on it.
So yeah, these are you know, typical questions in this area of study, and some of them, you know, start off as just kind of like, I wonder, you know, if this sequence ever terminates. I wonder if numbers have this property. But sometimes they can lead to really interesting discoveries. So someone posted a video on this conjecture on YouTube, so I'll have to check that out later. All right, so probably the most famous of these, and I'm guessing a lot of people here have already heard of this, Fermat's last theorem. So give me a thumbs up if you've heard of this already. It's pretty popular material for, you know, it pops up in Star Trek and all kinds of other shows. Yeah, we got some thumbs up. So here's the deal with Fermat's last theorem. You're familiar with the Pythagorean theorem. So if you have a triangle with lengths AB and hypotenuse C, it satisfies this property: a squared plus b squared equals c squared. That's true for triangles. And an interesting question is, when does this work where each side of your triangle is an integral length? In other words, when do you have integers that satisfy a squared plus b squared equals c squared? And the Greeks study this. These are called, Pythagorean triples. And for example, 3 squared plus 4 squared, that's 9 plus 16 is 25, that's 5 squared. 5 squared plus 12 squared, that's 25 plus 144, that's 13 squared, 169. And there's a whole bunch of triples of integers that will satisfy this equation. And these represent triangles whose lengths are all whole numbers. And that's part of why the Greeks were interested in these and why they studied them, because they liked whole numbers. And so when can you make a right triangle with all three sides being whole numbers? So there's an infinite number of solutions to this equation. And so an interesting question is, what about this equation? A cubed plus b cubed equals c cubed. And, if we don't restrict ourselves to integers, we can certainly solve this. I could make a1 and b1 and c the cube root of 2. And, yeah, this will be satisfied. And there's a few silly solutions, right? For example, 0 cubed plus 0 cubed equals 0 cubed. Or 1 cubed plus negative 1 cubed equals 0 cubed. There's some sort of uninteresting solutions. But if we require interesting solutions, so where our integers are positive, right? People wondered, is there a solution to this equation? And people tried to find solutions to it. People tried to prove there was no solution to it. And so Fermat, a mathematician, was reading a book that talked about these equations and general forms of these, something called Diophantine equations, which are just, equations that you try to solve with whole numbers, integers. And he was reading a copy of a textbook that he owned in a chapter that talked about Diophantine equations, and it mentioned this equation. And in the margin of that book, he scribbled a note to himself. And the note said, this is a fascinating idea. In fact, there is no solution in integers to this equation. And he wrote this equation down and said, you could not solve this with integers. And he said, I've discovered a splendid proof of this fact, which is too large to include in this margin. But he was kind of writing a note to himself. Well, instead of developing that proof and publishing it, he passed away. And after his death, somebody found his copy of this book, and while flipping through it, came across this section with this equation, and his note saying, you could not solve this with integers, and he had a proof of it. But there was no proof in the margin, because the margin was, too small. And so people called this Fermat's last theorem, the proof that you could not solve this equation. And he even went further and said that the general equation a to the n plus b to the n equals c to the n, where n is bigger than 2, you could never solve that. For cubes, for fourth powers, for fifth powers, couldn't do it for any power bigger than 2. So he said he knew how to prove it, but there was no proof. And so this became known as Fermat's last theorem. And it more formally says, there does not exist a, b, c in the set of positive numbers such that a to the n plus b to the n equals c to the n, where n is bigger than or equal to 3. And so people decide... Say again?
The splendid proof you mentioned, did he ever write it out?
Not that anybody ever found.
Didn't somebody disprove this? They found some absurd combination of integers that were 20 digits long that disproved this.
Well, people have chased this problem ever since. And at first it was Fermat had a proof, let's figure out what that proof was. And people sat down, and started trying to scribble together proofs and discovered this was a really hard problem to break into. And they were trying to solve it for cubes, right? A cubed plus b cubed equals c cubed. And for a long time, that was an open question. And somebody eventually proved that you could not solve this with cubes. But to do the general question with, any integer n bigger than or equal to 3, that was elusive. And for, hundreds of years, people worked on this problem, and cash prizes were offered if somebody could either prove that this was true or find numbers a, b, and c, and n that satisfy this equation with integers. What's really cool is that over the centuries, people often thought they came up with a proof. And they would get excited, and they'd publish the proof, and people would read it and get all excited. And then eventually, somebody would read the proof really, really carefully and discover a problem with it. And they'd say, oh, you assume that all squirrels eat walnuts, but the such and such squirrel despises walnuts. And the whole proof would fall apart. And then people would set off and try to fix that proof. And entire branches of mathematics have been developed through this process, just trying to fix up defective proofs of Fermat's last theorem. So this was finally proven to be true, and it was proven in the early 90s. And the mathematics involved in proving it are way beyond anything that was known in Fermat's time. So the general assumption is Fermat did not actually have a proof. He probably outlined something in his mind, but made some assumptions that if he had actually tried to turn it into a proof, he would have discovered a problem with it. But this was finally proven in the affirmative that you cannot solve this equation for n bigger than or equal to 3. And that was someone named Andrew Wiles, and there was, big cash award and lots of publicity and all this kind of stuff. So, but that's a pretty recent achievement at the end of the 20th century. But again, it's such a simple question. Can you find whole numbers where this is true? And trying to dig into that is like so phenomenally difficult. So you can find lots of material on this. There's a really cool book called Fermat's Last Theorem that gives you a lot of the colorful history of this, as well as some of the science behind it. All right, so let's go back to operations that we want to do on numbers. And I want to talk about something called the greatest common factor, or greatest common divisor. And we encounter these, in school when we learn about fractions. So you're trying to add fractions or multiply fractions or things like that, and maybe you come up with an answer like 25/10. And chances are, if you turn that into your teacher, you don't get a little gold star on it because you didn't reduce it to simplest terms, right? If you've been told to do that. So this is the same thing as this. Well, why is that? Well, I divided the top and bottom by 5. And so, that's something you learn to do in school. When you have an answer for a fraction, you should always reduce it. The question is, how did I know to divide the top and bottom by 5? Well, if I divide it by 1, it doesn't change anything. If I divide it by 10, I get something like, 2.5 over 1, and my teacher's not going to like that. But 5 is this magic number that if I divide, I get an integer on top and an integer on bottom, and there's nothing I can do to this to make it simpler. Now, if I had a fraction like 30 over 10, and I divided by 5, I would get 15/5. But that's still not in simplest form, because there's still a common factor for both of these. I can divide the top and bottom by 5, and write this as 3 over 1. Now, if I had known that the greatest common factor between these two things was 10, I could have just directly divided the top and bottom by 10. So there's this general question of, if you're given two integers, what is the greatest common divisor? And so this is the largest int, n, such that n divides x and n divides y. And so, for example, the greatest common divisor of 25 and 10 is 5. The greatest common divisor of 48 and 6 is 2. No, it's not. It's 6. The greatest common divisor of 48 and 10, that turns out to be 2. And a lot of times it's useful to know what the greatest common divisor is between two things. For example, if you're writing a program in a computer to work with fractions, something you might do in 223, hint hint, you know, you add fractions, you multiply them, and so on, and you end up with things like this. Well, you need to reduce them, right? Otherwise, you end up with, you know, 25 billion over 10 billion, right? And that should just be 5 halves. So this is a useful thing to be able to do. It also pops up in crypto systems a lot. And so there's an algorithm we can use for finding the greatest common divisor. And this is called Euclid's algorithm. And so you definitely want to know Euclid's algorithm. So this will be on a future homework. It'll be on future tests. It will come in useful all over your life, possibly, depending on what your life is like. So how does this work? Let's find the greatest common divisor of 48 and 10. All right, so this is just an algorithm that we do as people. We can teach a computer to do this too. Take your larger number, write it as something times your smaller number plus something left over. Now, if this is divisible by 10, just divide by 10, and you know, this is your largest common divisor. But assuming that 48 is not evenly divisible by 10, there's going to be something left over. So 48, I can put 10 into it 4 times. I can't do it 5 because that's 50, which is too big. But I can put 4 into it 10 times, and I have 8 left over. All right, I'm going to take the 10 and put it down here, and I'm going to take the 8 and put it down here, and I'm going to write a second equation. I'm going to say 10 equals something times 8 plus something left over. All right, in this case, 10 is equal to 1 times 8 plus 2. I'm going to write a third equation. I'm going to say 8 equals something times 2 plus something. Well, now 8 is equal to 4 times 2 plus 0. Once I see this 0, my answer is right here. So the GCD is going to be equal to 2. All right, do you want to try it again? So let's do 735 and 252. So 735 equals 2 times 252 plus something. I'm going to be lazy. So it's got 231 left over. Thank you. And now I'm going to write 252 equals something times 231 plus something. Well, I can see this is only going to go in once, and it's going to have 21 left over. And so now I'll write 231 equals something times 21 plus something left over. And it turns out this goes in exactly 11 times with 0 left over. There's my 0. That tells me I'm done, and my answer is this last remainder that I multiplied by. And you can always check your work, right? If I say, okay, 21 is the greatest common divisor, I should be able to take 735 and divide by 21. I should be able to take 52 and divide by 21, and I better get integers. Now that doesn't guarantee my answer is right, but if I thought, 11 was my answer, I could do 735 divided by 11. Right there I know I made a mistake, because 11 is not a divisor of 735, so it can't be a common divisor. So then I go back and I check my notes and I think about it. It's like, oh yeah, this is the answer, not that. Right? So you can always kind of sanity check your results. Alright, so that's a useful algorithm to know. And like I say, there'll be homework questions for it next week. They'll let you practice that. And it's a pretty well-behaved algorithm. If I happen to do things backwards, if I happen to find, greatest common divisor of 10, 35, well, I would say let's write 10 equals something times 35 plus something. Well, 35 goes into 10 0 times, and I have a total of 10 left over. And now I come down here and I say let's write 35 as something times 10 plus something. Well, that's what would have been my first step if I'd done, GCD of 35 comma 10. So if I happen to forget that I should do the biggest number first, it's okay. And this goes in 3 times and you've got 5 left over. And then you write 10 equals something times 5 plus something. And this goes in 2 times with 0 left over, so there's your greatest common divisor.
That's pretty cool.
Yeah, it's not bad. It's pretty easy to teach a computer to do it. And as long as you can calculate things modulo something else, it's pretty easy to apply.
How much faster do you think it is than just trying all the numbers below the denominator?
Oh, that would be tricky. I mean, that's a brute force way to do it. So you could pick the smallest number and, start with that and work your way down to 1 and find the first number that divides the bigger number. So I try dividing 35 by 10, 9, 8, 7, 6. When I get to 5, it divides. I'm done. That's the biggest common divisor. But for a number with 100 digits, it's probably not going to finish anytime reasonably soon. So once we know GCD, we can talk about the concept of relatively prime. And so this is just a definition. A and B are relatively prime if their greatest common divisor is 1. Now we know 1 is always a common divisor. 1 will certainly divide A and B, but if that's the largest number that divides A and B, then we say that these are relatively prime. And the idea is, if P is prime and Q is different from P, GCD of P comma Q is guaranteed to be 1. Well, and P does not divide Q. Unless this is a multiple of P, the only factors of P are 1 and P. So 1 will divide Q, but if P does not divide Q, the only factor in common is going to be 1. So primes, we're kind of special like this, but even if we have 2 numbers that are not prime, they could be relatively prime. So the greatest common divisor of 4 and 27 is 1. There's no other number that divides both of them. Other than like -1, but that's smaller than 1. Similarly, if I pick a prime number, P, the greatest common divisor of P and P is 1. if P is not prime, well, no, never mind that. Forget that. I could make that work, but it's not worth it. All right, so these numbers are called relatively prime, and we'll touch on those when we do RSA public key encryption next week.
Is that like coprime?
I think that's like coprime.
Where they just curve like almost prime or something like that.
I gotta look that up actually. All right, one other result I want to mention to you. We're not going to prove this. We're not going to go into the details of how to apply this. But I want to mention something called the Chinese remainder theorem, because this will come up in our public key crypto discussion. But Chinese remainder theorem is, you know, you've done simultaneous equations. When you do KVL, KCL, your problem ends up with, you know, solve these 3 equations and 3 unknowns. Well, it's interesting to think about trying to solve simultaneous equations involving integers. And so here's an example. Find an integer x such that x is congruent to 2 modulo 3 and x is congruent to 3 modulo 5 and x is congruent to 2 modulo 7. And there's an ancient Chinese text, a few thousand years old, that mentions this question, which is basically a question of simultaneous congruence equations, looking for a number that's 2 more than a multiple of 3 and 3 more than a multiple of 5 and so on. And so the question is, you know, is there an integer that satisfies all 3 of these equations? And if so, you know, what's the smallest such integer?
Smallest integer of what? Sorry?
That satisfies all 3 of these equations.
Oh, I see.
And it turns out 23 is a solution. So 23 is 2 more than a multiple of 7, right? 23 minus 2 is 21. That's divisible by 3, not 7. 23 minus 3 is 20. That's a multiple of 5. And 23 minus 2 is 21. That's also a multiple of 7. And so this value of x satisfies all 3 of these equations. So the Chinese remainder theorem, and you'll see this written up as just CRT. CRT tells us when a solution exists to a set of equations like this and tells us how to find that solution. And I'm not going to go through that algorithm. You can find it all different places online. But I just want you to know that it exists and there is a way to solve these equations when there is a solution. And that technique is called the Chinese remainder theorem. All right. Last theorem I want to talk about is something called Fermat's little theorem. And it's the same initials as Fermat's last theorem, but this theorem was proven by Fermat, I believe, and it's an accepted theorem. And this is related to finding exponents of numbers modulo something. And so remember we talked about modular exponentiation. If you wanted to find, you know, x to the y, you can write y out as, you know, 1 plus 4 plus 16 plus 32 plus 128. Find powers of x that are powers of 2, x to the 1, x squared, x to the 4th, x to the 8th, and then add up those subpowers. So that was something we called modular exponentiation. This is a different approach we can use to do fast exponentiation. And Fermat's little theorem states the following. If p is prime, and if a is not a multiple of p, if a is a multiple of p, this next part becomes silly. But if P is prime and P does not divide A, then we have the following wonderful result. A raised to the P minus 1 is congruent to 1 modulo P. All right, so what does this mean? For example, somebody pick a prime. Tell me your favorite prime. People don't have favorite primes.
23.
23, cool, thank you. All right, and somebody pick a value of A that's not a multiple of 23. Positive number.
Is that anything?
Yeah, any positive number.
6.
6, cool. All right, so this claims that 6 to the 23rd should be one more than a multiple of 23.
Or you mean 6 to the 22nd?
Yes, thank you. 6 to the 22nd should be one more than a multiple of 23. So there's 6 raised to the 22nd. There's 6 raised to the 22nd minus 1. And if we divide this by 23, it's an integer. But without doing those calculations, without calculating this number, without trying to do division, we can say absolutely this is going to be a true fact. That's what Fermat's little theorem tells us. All right, why do we care about this? Because 1 is a really nice number. In particular, if I want to raise 1 to the billionth power, I don't have to do any work. I can just say it's 1. That's one of the things 1 does. So suppose I wanted to do 6 raised to the 225th modulo 23. For some reason, you know, someone wants to know what this is equal to. All right, here's what I can do. I can say, you know, by Fermat's little theorem, 6 to the 22 is congruent to 1. Well, 6 to the 220th is congruent to 6 to the 22 times 10, which is congruent to 6 to the 22 raised to the 10th, which is congruent to 1 to the 10th, which is congruent to 1. So I just did the labor of multiplying 6 by itself 220 times, dividing by 23, and without doing all that, I know that this is one more than a multiple of 23. Now, if I want to know what 6 to the 225th is, I don't have to do too much work now. I got to do a little more work than I wanted to. This will be 6. 6 to the 222 will be congruent to 6 times 6, which is 36, which is 13 more than 23. I'm going to save myself some time. Suppose I wanted to know what 6 to the 222nd was, right? We just calculated that it's congruent to 13. So 6 to the 222nd minus 13 is this big long number. And if we divide that by 23, we get an integer. So Fermat's little theorem lets us cut through large numbers of exponents to answer questions such as, you know, what is this congruent to? Modulo that. And this works, you know, as long as this number is prime and this is not a multiple of this number. Now, if this was a multiple, if this was like, you know, 46 or 230, well, those are congruent to 0. And so when we raise that to a big number, it's still congruent to 0. So in the uninteresting case, this doesn't work. But as long as this A is not a multiple of P, then this fact holds. All right, questions about that?
Sure I will when I try it on the homework. But
Okay.
actually, okay, here I have a question.
Okay.
You have, oh wait, no, wait, 220 and then 200, or 2,240? 2,200,
Oh,
is that 2 zeros?
6 to the 22 times 10. Right, because 220 is 22 times 10.
Okay.
Yeah, I came kind of small. So if this is a multiple of 22, then 6 to that will be congruent to 1. Because it's 6 to the 22 raised to whatever that multiple is.
I see. Okay.
All right, so let's talk about applications for all this. Why do we care about any of this stuff? Why do we care about modular arithmetic or greatest common factors or things like that? So there's lots of places where these things pop up. If you're in CSE215, we've been talking about hash tables and hash functions, and our hash functions inevitably involve a modulo operator. We hash a key to an index, and that index could be bigger than the length of the hash table. So we reduce it modulo the length of the hash table. We get a number between 0 and that length minus 1. That's our index into the array. If you're not in 222, don't worry about that. But other applications, so one good example of this is parity generation and checking. So what is parity? Go back to, like the 60s or the 70s, early days of connecting machines together, computers and such, and early networking was done over phone lines, right? So there were already telephone lines, in the walls of buildings and down the streets, and so you could connect machines together once the phone company allowed it with by using the phone lines. And the earliest technology for this was done using sound waves. And so there were things called acoustic couplers, and this is a pretty typical example of what one looked like. I actually worked with one of these a lot. It was this funny looking device that had two spongy rubber things on here that would hold the handset from a telephone. So, think of a corded phone that you hold up to your ear and your mouth, and this is the end that you talk into, this is the end you listen to. Well, you would dial up the number of the computer you were trying to connect to, and something on that end would answer the phone, and it would make beeping noises. And when you heard the beeping noises, you would take the handset and you'd put it into this contraption, and it would beep, through this part of it, and the phone would listen to it. And if the phone generated, if this thing generated noise, it would go into this part of the phone and be transmitted down the phone lines. And this is how networking was set up, right? And this was convenient because, there were phones in offices and computer rooms and stuff like that, and you didn't have to actually, connect to the physical copper, and legally, eventually, you could send any information over the phone as sound. You could send any information you wanted, but you weren't allowed to actually, plug something into the phone jack in the wall. That came much later. But being able to send tones over the phone was a breakthrough. And so the idea was people would use acoustic couplers to send information from machine to machine by sending different tones. And so those squeaking sounds that you hear, with old dial-ups, or if you hear it in like remixed techno music and stuff, those were ways of coding binary information. All right, well, here's the deal. So let's say you're sending a character. You want to send a grade in. So A is ASCII code 65. And so you would send this as, as this binary number. And the way you would send a piece of binary information is you would use a high tone or a low tone to represent a 0 or a 1. And so it was actually backwards from what I'm going to draw, but I'll draw it like this. This would be a 0, a 1, a 0, a 0, a 0, a 0, a 0, and then a 1. And everything was time-based, so you'd have to know to sample right at these points. And so an A would be, a high tone, a few low tones, and then a high tone. Well, this is all sound waves going across, an old-style rotary telephone. And, if a car backfired outside, there might be a loud noise generated that might get through those, spongy cylinders that you were putting the hand receiver into. And it's possible that your signal might sound like this on the other end, right? This might mistakenly come out as a 1. And this would be the binary pattern, like this. And that's a coding for a 67, and that's a C. So if I meant to type in somebody's grade, which was an A, and while I was, having those bits sent over the machine, some noise happened, or somebody picked up the other extension and made a noise, or there was just a glitch in the system, a stray click or something, it's possible that the computer thought it saw this information, which was a C. And now it's recorded the wrong grade for somebody. So that's a problem. And these old systems were so noisy, and it was so easy to flip the bits by mistake, that, they couldn't be used for communicating information. So one way to deal with this is to generate what's called a parity bit. And so let's say we're going to do even parity. Well, here's the idea. Take the sum from I equals 0 to 7 of bit I, and then add the parity bit, and then take all of that and reduce it modulo 2, and see if the result is equal to 0. And if it is, you have a good number. So before I send information, I tack one extra bit on. And I tack an extra bit so that the sum of all 9 bits that I send is divisible by 2. So the parity bit would be the sum of bits mod 2. So here's the 8 bits I want to send. 0, 1, 0, 0, 0, 0, 0, 1. Add up those 8 bits, I get 2. 2 modulo 2 is 0. So my parity bit would be a 0. On the receiving end, the computer receives these 9 bits, adds them up, finds a 2, reduces that modulo 2, gets a 0, checks to see if it's 0, yes it is, says that's a good number. Now if I send this exact same 9-bit pattern, but this bit over here glitched, now the receiving computer is going to see 6 zeros and 9 ones, or 3 ones. When it adds up all 9 of these bits, it's going to get a 3. When it takes 3 modulo 2, it's going to have a remainder of 1 that's not equal to 0. It's going to say something's wrong. So it generates what's called a parity error, and it sends a signal back to whoever sent that information and says, I didn't hear you clearly, please resend. And so the computer would send this information out again, and presumably, if it gets there correctly, these bits add up to a multiple of 2, and it says, okay, I got you, and you go on. And so every character that was sent had this extra bit, and this check would take place. And it's a pretty nice system. It's pretty easy to generate, right? Do some addition, do some modulo arithmetic. And if I wanted to send this, and I accidentally flip the parity bit, that's also going to generate an error. Right? If my data is correct, but this bit gets perturbed for some reason, well, the receiving machine would add these up, get a 3, 3 modulo 2 is a 1, that's not 0, there's a problem.
The problems start happening when more than one of the bits get flipped?
But problems definitely happen if more than one of the bits get flipped. Because, for example, if I want to send this and I accidentally send this, right, my parity bit I generate will be a 0 because I've got 1, 2, 3, 4 ones. And on the receiving end, I'll add up these 9 bits. I get 4 modulo 2 is 0. That's what it should be. Hey, that's a good number, right? But this is definitely not the same number as that. So this does not work if you have more than one bit flip. So in a very noisy environment, it's going to catch some of the errors, but not all of them. The other problem is, you know, if it does catch an error, it doesn't tell you anything about where that error is. Really, all you can do is say, I didn't hear you clearly, and ask the sender to resend the information. But nonetheless, this worked pretty well for a long time. And for odd parity, we do exactly the same thing, but we want the remainder modulo 2 to be 1. And sometimes odd parity is a little bit safer, because here's a really common failure mode. What if everything you send comes out as 0? Because maybe, you know, your speaker failed, and so you're always sending zeros. Or, you know, the channel going to the modem has been shorted out to ground. Well, if I look at this and I add up the bits and reduce it modulo 2, I get a 0. Hey, this looks like a good number. So sometimes you would do odd parity, where you insist that the sum of all 9 bits is 1 more than a multiple of 2. So congruent to 1 mod 2. And even in modern terminal programs, for, like, you know, talking to serial ports through a USB or something, you can still find settings for, you know, do you want to generate parity? And do you want even parity or odd parity? And it's not really used much anymore. It's kind of a holdover from before, but it's still in a lot of the software we use. But it does have this problem that if 2 or more bits flip, it may not catch it. If 3 bits flip, it'll catch it. But 2, which is, you know, the most common error after 1, it won't notice. So there's other versions of this. A popular one is, you know, ECC. And so memory, you used to be able to buy, you know, slightly cheaper memory that did not have error checking on it, or slightly more expensive memory that did. And so ECC is a way to take 32 bits of information and add 3 check bits, I believe it's 3, and this will detect a certain number of bit flips, and it will actually be able to correct some number of bit flips, not as many as it can detect, but at least 1 or 2. So they can say not just, you know, there's a problem with these bits, but it can say, oh yeah, there's a problem. That bit that's a 0 actually should be a 1. And so as memories got denser and smaller and started working with lower voltage, they became more and more error prone. And it got to be where your memory would just have lots of errors in it. Radiation coming in from the sky would, you know, hit the capacitors and a bit would flip. And so error checking and correcting codes started to appear in, you know, DRAMs that you would buy for computers. And it gives you some measure of protection against these kinds of errors. CRC, cyclic redundancy checks. You saw these on hard drives for a while. Because a hard drive, right, you're just pulling out tons of information from it. A sector on a hard drive might have, you know, a few thousand bits stored on it, typically a lot more. And, you know, if someone hands you a basket with, you know, 10,000 bits in it, how do you know if any of those bits are wrong? So CRC is a way to take those bits and generate some value associated with it. And then when you hand that basket of bits to, you know, the receiving end, you say, oh yeah, go ahead and do that calculation. You should end up with a number 23. And they can do that calculation. If they end up with 23, they feel pretty good, like those bits are correct. But if they end up with, you know, 512, instead of 23, they can say, hey, something's wrong. One of those bits got corrupted. And this starts to lead into things that we see today, such as MD5 hashes. So when you download a file from the web that you're going to run on your machine, how do you know that you should trust it? Right? So you've read about a program, a game, or a utility or something, you're like, that sounds really cool, and it says, you know, follow the link to download it, and you click on that link. Well, how do you know that you're downloading a good copy of this thing? How do you know that this hasn't been replaced by some piece of malicious software? And so typically, when you read information about a program, there'll be something like what's called an MD5 hash. And it's a big number, it might be like, 512 bytes or something, that is generated based on the bits inside the executable file. And when you download an executable, you can regenerate that MD5 hash and compare it to what you've been told that value should be. And if any of those bits got changed, almost guaranteed the number you get from this calculation will be different. And then hey, someone changed the code, or it got corrupted when I downloaded it. And so the algorithms for generating these are all just, applications of the kinds of things we've been doing and talking about number theory. Various calculations, almost always reducing things modulo something, in a way so that, you can take a 2 gigabyte file and produce a kind of fingerprint for it that might be, 500 bytes. But done in a way that if, one bit of this file changes, you get a totally different fingerprint. And if you deliberately change one bit of this file, it's almost impossible to figure out what else you can change in the file to restore the original fingerprint. And that's the real power of these sort of one-way functions. All right, so Monday I'll talk about a few more applications. I'll talk about things like UPCs, universal pricing codes, and ISBN numbers on textbooks and things like that. And then I want to finish up by talking about cryptography. And it's going to be a really, really brief high-level overview of cryptography. You can take crypto courses at university and get into a lot of the really deep, interesting material. But we'll do a pretty brief high-level pass over the subject and just kind of think about major themes. And then we'll run through this RSA public key crypto system just to let you see that, there are applications for all of these kind of unrelated seeming parts that we've been discussing. Fermat's little theorem, Chinese remainder theorem, and so on. We'll see how those all come together to work for public key crypto systems. ECC might be industry standard by now. I haven't bought memory in a long time. It almost has to be.
The consumer market.
Really? Wow. Okay. I don't know how you run memory like that.
Found by the CPU manufacturers for the last decade.
Interesting.
ECC memory. That's one of the reasons why it never took off in home computers, because it's been locked down by the chip manufacturers like Intel and AMD.
Interesting.
I see.
All right, cool.
For their server products to raise the price.
Yeah. All right, so we are out of time, so I will leave it at that. We'll meet back again on Monday. I'll get exams graded and posted as soon as I can. It'll probably be a few days, but like I say, if you're dying to know about some of the answers or want to talk about the exam in general, come by office hours if you like, Thursday or Friday, and we can talk then. Otherwise, have a great one, and I will see you next time.